Hello everyone, and welcome back to the AI Tools Research Channel. I am your host, Zeb Badi, and this video is about evaluating large language models. Many of you may have observed the recent acceleration in the quest for generative AI market share by the tech giants. After OpenAI's release of ChatGPT 3.5 in November of 2022, and then soon after ChatGPT 4 this year, other well-funded companies like Google, Meta, Microsoft, Apple, IBM, etc., have released their own LLMs. But how do we gauge the strengths and weakness of these models? What factors and metrics can we go by to measure their performance and their best use cases? Today, we'll be delving deep into the factors that contribute to the effectiveness of different large language models, so that you have some yardstick to evaluate, measure, and appraise them. We've got a lot to cover, so let's jump right in. Number 1. Size of the training data sets. First, we need to consider the size of the training data that the model learned from or was trained on. This is also called the corpus size. It's quite simple. The larger the amount of text data the model is trained on, the more accurate and comprehensive its understanding of language will be. Bigger is generally better in this case, but it's not just about having a vast quantity of data. There are other factors besides sheer volume of data, as we'll see later on. For example, PaLM 2, Pathways Language Model 2, used in Bard chatbot from Google that was released in May of 2023, has a corpus size of 3.6 trillion tokens. A token in this case is a word. Another recently released LLM by Meta, called Llama 2, was trained on a corpus size of 2 trillion tokens. The exact size of the training dataset of OpenAI's GPT-4 is not publicly known, but it is likely to be in the terabyte or petabyte range. This is a massive amount of data, and it required a significant amount of computational resources to train. The large training datasets also allow the LLMs to generate text that is more realistic and coherent than previous language models. They can also answer questions more accurately, and the answers are more comprehensive. They can generate more creative and informative text since they have a wider range of vocabulary and grammar rules. Overall, large training datasets are a major advantage, but they can also have some drawbacks. For example, large training datasets can make the LLM difficult to train and fine-tune, and it can also make the model more prone to biases. Also, it's about capturing as wide a range of linguistic diversity as possible. This allows the model to encounter and learn from a variety of language uses, dialects, styles, and genres. A large dataset without these attributes may be less effective than a smaller, diverse dataset. Some argue that the benefits of a massive training dataset outweigh the drawbacks since it makes the model more versatile and can be used for a variety of tasks. Number 2. Number of training parameters. You may have heard stuff like, the training dataset for Llama, large language model from Meta, is 70 billion parameters. Then comes along OpenAI with GPT-3 that has 175 billion parameters. Google won't be left behind, so they come up with PaLM 2, Pathways Language Model 2, that has 540 billion parameters. And wait, OpenAI's GPT-4 trumps PaLM 2 with nearly 1 trillion parameters. Although this is not official, but according to leaked information, since GPT-4 has kept this piece of information confidential. There are different types of parameters which play different roles in machine learning, and they are all important for the performance of the model. The first and the most important one is the model parameters. These are the values that are learned from the training data. They are the weights and biases of the model's neural network, and they determine how the model will make predictions. Next is hyperparameters. These are the parameters that control the learning process. They are not learned from the training data, but they need to be set before the model can be trained. These parameters include the learning rate, the number of epoch, batch size, and the dropout rate. Carefully established and set hyperparameters can significantly influence the accuracy and speed of the model. Then we have feature parameters. These are the values that represent the features of the data. They are typically used in conjunction with model parameters to make predictions. Finally, there are regularization parameters. These are used to prevent overfitting. They are typically added to the loss function, and they penalize the model for having large weights. There are a few other categories of parameters that are used in transformer-based LLMs, such as positional parameters that help the model understand the order of words in a sentence, attention parameters that allow the model to focus on specific parts of a sentence when making predictions, layer normalization parameters that help to normalize the activations of the model, which can improve the performance of the model, and dropout parameters that allow the model to randomly drop out some of its connections, which can help to prevent overfitting. Overfitting is a machine learning concept that refers to the situation where the model fits the training data so well that it cannot generalize its predictions for unseen data. Remember, large language models are not supposed to have a specific goal. Their job is to be very general, which means they are designed to predict what comes next, and it is okay if it's not exactly correct, because that is how language works. LLMs are trading accuracy for generality. Overall, the above parameters in a LLM are used to control the different aspects of the model. They allow the model to understand the order of words, focus on specific parts of a sentence, and make predictions. A model with more parameters can learn more complex relationships between words and phrases. This means that the model has been trained on a much larger and more diverse set of data, which allows it to generate more accurate and informative text. The relationship between the number of parameters in a language model and the size of the training dataset is not linear. A model with twice as many parameters does not require twice as much training data. However, in general, a larger training dataset will allow a model to learn more complex relationships between words and phrases, which can lead to improved performance. But the large number of parameters also has some drawbacks. It can make it more difficult to train and fine-tune the model, and it can also make the model more prone to biases. In summary, the number of parameters in a model is a measure of its complexity. A model with more parameters can learn more complex relationships between the features and the target variable. However, a model with too many parameters can also be an overfit to the training data, which means that it will not generalize well to new data. So, optimizing these parameters is key to building a powerful and effective LLM. Number 3. Quality of the training data. Here is where the adage garbage in, garbage out really applies. The data needs to be accurate, relevant, and importantly, diverse. It should mirror the language used in real-world scenarios and not be skewed or biased. Most LLMs training is done on datasets from the internet, Wikipedia, Books 1, Book 2, WordNet, etc., which are not curated. These datasets naturally contain a variety of data which includes a lot of junk, garbage, fake information, and even offensive and abusive stuff. To LLMs, all data looks the same. No LLM, at least not as yet, and nor in the near or intermediate future, will have the intelligence to distinguish good data from bad by itself. AI models do not have any reasoning capabilities like humans do as yet. This may change in 10 to 15 years when AI enters a more advanced stage of artificial general intelligence, the stage where AIs start reasoning like humans do. But until then, humans have to curate the mountains of data, which is near impossible. So for now, the models also learns to generate inaccurate and/or inappropriate content, along with the good stuff. This can be a problem if a model is used to generate text that is intended to be informative or helpful. For example, if a model is trained on a dataset of Wikipedia articles, it may learn to generate text that is factually incorrect or misleading. Second, because models cannot distinguish between good and bad information, it can be a problem especially if it's used to answer questions or provide information. For example, if a model is trained on a dataset of news articles, it may not be able to tell the difference between a reliable news source and a fake news source. Third, the presence of offensive data in the training datasets can make the model more likely to generate text that is offensive or harmful. This can be a problem if the model is used to interact with people, such as in a customer service setting. For example, if a model is trained on a dataset that contains social media posts, it may learn to generate text that is racist, sexist, or otherwise offensive. There are a number of steps that can be taken to mitigate the negative effects of junk, garbage, fake information, and abusive stuff in the training data for LLMs. These include filtering the training data. This involves removing any text that is obviously junk, garbage, fake, or abusive. This can be done manually or using automated tools if the company building the model is willing to spend the time, effort, and money. Labeling the training data. This involves assigning labels to each piece of text in the training data, indicating whether it is good, bad, or neutral. This can help the model to learn to distinguish between good and bad information. Using a variety of training datasets. This can help to reduce the impact of any individual dataset that contains junk and/or fake information. Using regularization techniques. These techniques can help to prevent the model from learning to generate text that is too similar to the training data. By taking these steps, it is possible to reduce the negative effects of so-called bad data in the training datasets for LLMs. This can help to ensure that the models generate text that is accurate, informative, and helpful. On the other hand, too much censorship may impair the broad adoption and usage of the model. Number 4, model architecture. The model architecture plays the most important role in an LLM's effectiveness. Different architectures such as transformer-based models like BERT, GPT-4, and Transformer XL can handle different tasks with varying degrees of success. The model's architecture directly impacts its effectiveness, as it essentially provides the blueprint for how the model operates. Let's take the transformer architecture as an example. Transformer-based LLMs don't really have a goal. They are designed to be very general, and therefore are suited for more general tasks. Basically, they predict which word comes next, and it is okay if it's not exactly correct. You are trading accuracy for generality. This is also why a large language model that generates computer software code is usually always syntactically correct. There is very little chance that any code would have the wrong syntax. But what it gets wrong is the semantics because it does not have a model of the semantics. This is one major reason why techniques like reinforcement learning with human feedback, or RLHF for short, will produce responses better aligned in generating computer software code. GPT-4 has this key feature, and that is what makes GPT-4 such a powerful and versatile language model. Large language models are based around the notion of text patterns. When you're training a large language model, it is essentially learning. It is building a statistical model of the text. It's using the context of that in the case of natural language. It knows the role that a token plays. A token is essentially a word in the large language model world. This is how it knows the difference between a noun and a verb and what part of speech it forms. LLMs use this information in order to construct the statistical model. And so, what you see with large language models is that from the prompt, it can do a very good job of figuring out what comes next. This kind of technology is like a turbocharged autocomplete because it does an amazing job at guessing what comes next. Number 5, training methodology. The approach to training can greatly impact the effectiveness of the model. This includes aspects like optimization algorithms, loss functions, etc. Also, pre-training a model on a general task before fine-tuning it for a specific task can lead to better results. Number 6, inference efficiency. Inference efficiency in a LLM is the amount of time and resources it takes to process an input and generate an output. This is important for LLMs because they are often used in real-time applications, such as chatbots or voice assistants. There are a number of factors that can affect the inference efficiency of an LLM. These factors include the size of the model. Larger models are typically less efficient than smaller models. The number of parameters. The number of parameters in a model is a measure of its complexity, as mentioned earlier. More complex models are typically less efficient than less complex models. The input data. The type of input data can also affect the inference efficiency of a LLM. For example, text input is typically more efficient than image input. The hardware platform. The hardware platform that the LLM is running on can also affect its inference efficiency. For example, LLMs running on GPUs are typically more efficient than LLMs running on CPUs. There are a number of techniques that can be used to improve the inference efficiency of a LLM, including quantization. This is a technique that reduces the precision of the model's parameters. This can make the model less accurate, but it can also make it more efficient. Distillation. This is a technique that creates a smaller, more efficient model from a larger, less efficient model. This is done by training the smaller model to mimic the outputs of the larger model. Model compression. This is a technique that reduces the size of the model's parameters. This can be done by removing redundant parameters or by using a different representation of the parameters. The best way to improve the inference efficiency of a LLM will depend on the specific application and the hardware platform that the LLM is running on. However, the techniques mentioned above can provide a good starting point for how quickly the model can generate predictions, especially if real-time responses are required. Number 7. Domain-specific tuning. Fine-tuning a pre-trained model on domain-specific data can improve its accuracy and relevance for that particular domain. For example, Jasper is a language model specifically trained for content marketing. We have other examples where models are specifically trained for storytelling and authoring books, etc. Number 8. Training costs. The financial cost of training, fine-tuning, and maintaining the model, including hardware, software, and human resources, must be factored into the evaluation. LLM computational costs are measured in GPU HRs. For example, in 2023, computational cost of training a 12 billion parameter LLM is 72,300 NVIDIA A100 GPU hours. As of June 2023, the cost of NVIDIA A100 GPU hour is approximately 25 cents. Therefore, the dollar cost of training a 12 billion parameter LLM is about $18,075. Now compare this to the costs in 2020. In 2020, the cost of training a 1.5 billion parameter LLM was between $80,000 and $1.6 million. Advances in software and hardware have reduced the cost substantially since 2020. So you can expect larger and larger datasets with increasing number of parameters and lower inference costs in the next generation of LLMs. You can be assured that the race between the tech giants has just begun and the best has yet to come. And don't forget that China is in the race as well. We have not even mentioned the LLMs being developed by state-financed Chinese tech firms. Number 9. Multimodality. We also need to consider the concept of multimodality. Models trained to handle multiple types of inputs, such as text, images, audio, and more, are becoming increasingly powerful due to more powerful GPUs together with lower compute costs. A common method to create multimodal models out of an LLM is to tokenize the output of a trained encoder. Concretely, one can construct a LLM that can understand images. For instance, Google PaLM model was fine-tuned into a multimodal model PaLM-E using the tokenization method and applied to robotic control. Meta's Llama models have also been turned into multimodal models using the tokenization method to allow image and video inputs. GPT-4 can use both text and image as inputs, while Google Gemini is expected to be multimodal. Number 10, last but not least, prompt engineering, attention mechanism, and context window. Most results previously achievable only through costly fine-tuning of models can now be achieved through prompt engineering. In LLMs, the scope of a single conversation, more precisely, is limited to the scope of a context window. For example, the 117 million parameter-sized GPT-2 model has 12 attention heads and a context window of only 1K tokens. This makes the length of the conversation in GPT-2 very limited. GPT-3 has a 2K-sized context window, and GPT 3.5 has a context window sized from 4K to 16K. The largest model from OpenAI, GPT-4, has a context window sized up to 32K, and that is why GPT-4 can take in large paragraphs as input and summarize them. The length of a conversation that the model can take into account when generating its next answer is limited by the size of a context window as well. If the length of a conversation, for example with ChatGPT, is longer than its context window, only the parts inside the context window are taken into account when generating the next answer. Or, the model needs to apply some algorithm to summarize the two distant parts of conversation, where you then get into attention mechanism complexities. However, large context windows have their shortcomings, and higher computational cost is on top of the list. The possibility of diluting the focus on local context is another shortcoming. On the other hand, making context windows smaller can cause a model to miss an important long-range dependency. So balancing the two is a matter of experimentation and understanding of domain-specific considerations. In conclusion, in the world of large language models, these are the key factors for comparisons. There's no one-size-fits-all approach here. It's all about understanding specific needs and goals and adapting these parameters accordingly. For LLM architects, balancing and optimizing these factors and parameters is key to building a powerful and effective large language model. It's an intricate balancing act that demands careful consideration of all these elements. Thank you for joining us on this deep dive. If you found this video helpful, remember to like, comment, and subscribe for more insights